Hello everyone, in this video we will solve a system of three equations in three variables using Gaussian elimination. Along the way we will also learn how to set up the augmented matrix for a system and how to reduce it to row echelon form. First, we need to represent the given system with an augmented matrix. To construct such an augmented matrix, create a coefficient matrix from the coefficients of the variables in the system, as well as a constant matrix from the constants on the right-hand side of the equations. Note that the first column contains the coefficients of x1 from each equation, the second column contains the coefficients of x2, and the third column contains the coefficient of x3. On the right-hand side, we will have the matrix of constants of the equations. The matrix on the left is called the coefficient matrix, and the matrix on the right is called the constant matrix. Now, if we combine these two matrices into one, the resulting matrix is called the augmented matrix. Notice that this matrix has exactly the same information as the original system. The coefficients from one equation of the system create one row of the augmented matrix. Now, through a systemic procedure of row operations, we will simplify the augmented matrix and carry it to row echelon form. Note that the elementary row operations used on the augmented matrix will not change the solution to the corresponding system. We begin with the augmented matrix in its original form. Starting from the left, we find the first non-zero column. In this example, all columns are non-zero, and thus the first column is the first pivot column, and the position at the top of this column, which is 2, is the first pivot position or leading entry of row 1. The first step is to create a 1 in the upper left corner. So we multiply the first row by 1 over 2. This number 1 is called the leading 1 of the first row. Then we use this leading 1 to create zeros in the other positions of the first column, which are -2 and -5. This is done through row operations using the first row, which is the row that contains this leading 1. So we need to take 2 times the first row and add it to the second row to make -2, 0. 2 times row 1 is obtained by multiplying each entry of row 1 by 2. For adding rows, we simply add their corresponding entries. This is the new row 2 and will replace the original row 2. Next, we take 5 times the first row and add it to the third row to make -5, 0. This completes the work on column 1. We now move to the second column. The first entry of row 2 in this column is the leading entry of row 2, which in this case is -1. Similar to the previous step, we first make this number 1 by multiplying row 2 by -1. This is now the leading 1 of the second row. Next, we use this leading 1 to create 0 in the entry below it, which in this case is -1. This is done by adding row 2 to row 3. This completes the work on column 2. Then we move to the third column. -3 is the leading entry of row 3. We need to make it 1 by multiplying the third row by 1 over -3. This is now the leading 1 of row 3. This completes the work on column 3. Note that the resulting matrix has a staircase form, meaning that the leading entries of all three rows are 1, and they proceed down and to the right through the matrix. Also, all entries below and to the left of leading ones are 0. The matrix in such a form is called row echelon form. Finally, converting the row echelon form matrix to the system of equations, we obtain the following system. Note that the numbers in each row of the matrix correspond to the numerical coefficients of variables and the constant of each equation in the system. From the second and third equation, we obtain x2 to be 4 and x3 to be 6. Next, we substitute back the values of x2 and x3 into the first equation to solve for x1. Thus, the solution of the system is x1 equals -18, x2 equals 4, and x3 equals 6. Thanks for watching.